Okay, so on this lecture, today's lecture, I want to pick up in the same vein of what we have been discussing. So the first unit that this course has really been covering is software engineering principles, especially those software engineering principles that aid in developing software that can be reused by other developers. And so this is a programming methodology. This is a subdomain that I'll refer to as API programming. And so I want to cover one last set of tools, techniques, and approaches that will facilitate API programming, the API programming portion of this course. So it's a concept that's called defensive programming. And so you could think of defensive programming kind of as a companion to design by contract, which is, I believe, what one of the concepts that we initially opened up with for this course. So just a quick overview of what we'll be discussing today. Defensive programming, why program defensively, just a quick review on encapsulation and access restriction. And then what we'll do is we'll define and identify defensive programming and why it's important to us as developers. Then we'll look at two different approaches that we can utilize for defensive programming, asserts and exceptions. And then we'll take a deep look into exceptions, where we actually take and examine unchecked exceptions, checked exceptions, how we can JUnit test exceptions, exception handling. This will be really a deep dive into that. So you might have a shallow understanding of exceptions from the initial class from Java 1, but we're gonna see why we want to use exceptions in this class today. So first, let's talk about the motivation of defensive programming. So normally your classes will form part of a larger system. So other programmers will be using and rely upon your classes. So obviously your classes should be correct, but equally important, your classes should be robust. That is, resistant to accidental misuse by other programmers. You should aim to ensure that no errors in the final system can be attributed to the behavior of your classes, right? You're trying to keep yourself as a, you don't want to brand yourself as a troublemaker across the application design of your software. And so we use the terminology client code for the code that's written by other programmers that is using your class. And so that's probably a term you've heard me use multiple times, but I just want to formally define it here when we're talking about being defensive in our programming. So again, just a quick reminder of what encapsulation is. One of the most important features of object-oriented programming is that it facilitates encapsulation. A class encapsulates both the data it uses and the methods that manipulate that data. So the external user only sees those public methods of the class and interacts with objects of that class purely by calling those methods. And that's why in JUnit testing, the methods are the most elemental unit that we can evaluate and test, because everything in our software system is effectively doing message passing by invoking methods. This has several benefits. Users are insulated from needing to learn details outside their scope of competence, and programmers can alter or improve the implementation without affecting any client code. And so we enforce encapsulation with the access restrictions that we can assign to our data, to our fields, or to our methods. So encapsulation is enforced by the correct use of the access modifiers, public, private, and protected. So if you omit the access modifier, then you get the default, sometimes known as package access. These later two modifiers are only really relevant for multi-package programs that use inheritance. So we need only consider public and private unless you're doing package related task. But for the most part, this is just a quick reminder of what has motivated this design by contract. It's the fact that because of encapsulation, that we can restrict access to certain parts of our software system that resides within our, whether it's packages or class or whatever, we can then use our design by contract where we define those preconditions and postconditions. So like I said before, defensive programming is a companion to this design by contract, which we already covered. So design by contract establishes the preconditions and postconditions between the implementer and the client developer. If the client violates the preconditions, then the implementer guarantees nothing, right? But with defensive programming, we still go ahead and check the client's request, and we can alert them if they violated the precondition as a courtesy. So it's a good idea to go ahead and defensively anticipate that your client code might do something wrong. And so if they do, we can let them know. Or sometimes they might give us what is the precondition. They might give us everything in the precondition, but for a reason that they can't have avoided, they might we might not be able to process a result for our post condition. So if there is something that causes an issue that that we can't avoid, then we can also kind of be defensive on that as well. Okay. So design by contract is complementary to defensive programming because with preconditions, it makes clear which inputs to methods are unexpected. And with postconditions, it makes it clear when an internal bug has occurred, but it does not prescribe predictable behavior in the face or unexpected inputs and internal errors, right? So here we've created something that's well-defined, hence the term a contract between the two parties, the implementer and the user. But with defensive programming, we can start to handle things that violate that contract. So defensive programming is a loosely defined collection of techniques to reduce the risk of failure at runtime. One technique is making the software behave in a predictable manner despite unexpected inputs or user actions. And so related to this concept is making the software behave in a predictable manner despite internal errors. So let's take a look at an example. So consider this search routine. We have our requires, where A is not equal to null, and we have our ensures that states that there is an I such that A of I, so index of I into A equals X, implies that A result is equal to X. And there is no index such that A index of A equals X implies a result that it's within the len. Okay, so given the requires, so this is our precondition, and then this would be our post condition, the ensures. Inside of this search, we're just claiming that so long as our array is not null, then we will go ahead and produce some result. Either we will find the value you're looking for, or we'll get to the end of the array. Okay, so given this contract of preconditions and postconditions, suppose that we had Bob who implemented it like this. Okay, K equals 0, that's our indexer, our loop control variable. And while K is less than the length of the array, and the index of K into A is not the value we're looking for, we'll increment K. And then finally, we will return K. Okay, so that is an implementation that follows the initial rules for being able to search this array for that value. Let's see what alternative implementations we might have. So we might have Chris who had implemented it this way, very same method, but here we have an assert. So before we do any of the implementation that Bob had done, we will assert that A is not equal to null, right? That's the precondition. And then we're going to here assert that K is equal to A dot length, or K indexed into A is equal to X. So this is going to go ahead and evaluate the post condition. So the assert keyword, the assert method the assert keyword in Java will throw an exception if the condition is false, and assertion checking is enabled. So we'll talk more about asserts a little bit later, but this is more of a defensive approach to programming, where instead of just trusting that your client will fulfill the precondition, we can actually just check and assert that the precondition is met. And then we can even assert that the postcondition is met. Again, these asserts are really good for testing your own code base out while working on everything, since it will throw an exception if either of these conditions are violated. Okay, let's take a look at perhaps Dan's implementation. So Dan has a assert.check, and he's passing in A is not equal to null, and then a string that says searches precondition failed. And then here in the post condition, we have a assert check, and then the conditions on which the post condition would fail. And then the second parameter here is a search post condition failed. Okay, so what is this assert dot check that we're doing? Well, that itself is a class that Dan had made to assist his defensive programming strategy. So here, assert is a class, a user-defined class that has a static void check where a Boolean condition can be passed and a string. And if the condition, if it's not that condition, then you could throw a new assertion error along with the message. So this just controls. So this and this are effectively doing the same thing, but this is providing a little bit more information to the client. Again, so another way of defensively applying a defensive strategy towards your implementation. And then let's look at what Eve is doing. So Eve implemented it this way. So given the contract that requires and the insurers, we'll do a search. If A is equal to null, we're just going to return 0. And if it's not, then we will do the logic. So I want to illustrate that all of these implementations are for the same method. But if we were to evaluate which ones were most effective in terms of a defensive programming strategy, so they all meet the contract. Bob was not practicing defensive programming. Bob's implementation was just the pure implementation, trusted that the client would read the preconditions and postconditions. Chris and Dan were practicing defensive programming. One used assert, the other used a class that they created that would go ahead and use assert, but in a more meaningful way. And Eve was practicing poor defensive programming, because if you take the time to check a precondition, it's better to make someone aware of its failure. Here, Eve was checking, but was returning 0. But 0 is a valid value here. So that's even a worse thing to do, because perhaps the user would think that the double value that they're searching for is at index 0. It would be even better if Eve used a negative value, something that couldn't possibly be a real index, to alert the user that, hey, something went wrong. But better would be to actually just throw an error or an exception or something along those lines. So defensive checks such as assertions are analogous to fuses in a power circuit. They cause erroneous systems to fail fast, i.e. to fail before further damage is done. They also help pinpoint the root cause of a fault. A safety critical system should also fail safe. The combination of fail fast and fail safe, fault tolerance, which is a recovery from failure, and failure reporting is the best. And so these are all approaches we try to integrate as our defensive programming strategy. So again, Eve's solution was poor because it masked the earlier error as garbage in, garbage out solution. But what it's going to do is it's going to hide from the client code where their fault in logic is. So there's also this concept of partial checks versus full checks. So note that Chris and Dan did not check the post condition. Rather, they just checked an implication of the post condition. So that's what's considered a partial check. If you're just checking a precondition, or if you only check a part of the post condition, whether it is worth the computational design cost to check the full pre or post condition is a function of many inputs. So it's based off of the confidence in the code, the cost of what an error could produce, the cost of a partial check versus a full check, and the sufficiency of a partial check versus a full check. So you don't necessarily always have to check all of your post conditions or even your preconditions based off of this rubric. But look at this rubric, and if, say, for instance, the cost of error is high or the confidence in the code is low, then you'd want to do more evaluations. And if the confidence of the code is high and the cost of the error is low, then you might not care so much. So defensive programming and contracts, because I'm tying these two concepts together, defensive programming is complementary to the use of contracts. A contract obviously guides the writing of runtime defensive checks. A defensive check helps ensure that the contract is being respected. And some systems like, say, for instance, .NET, contracts can automatically turn contracts into runtime defensive checks. So there are some frameworks out there, we won't use any of them, that will actually use the contracts you define during your design and development phase as runtime checks that can throw things like exceptions or errors for you. And so when we're talking about defensive programming, a thing that I really want to hearken to you as another motivation is to discriminate between what are considered valid values and legal values. So as an implementer, what you're doing is you're typically you're data modeling something in your software environment, and you're presenting it as an object, as an entity. So we want to use these defensive programming as API implementers to ensure that the state of our data models remain valid. Because usually the underlying state of our data values ultimately translates into some primitive data type, whether it's an integer, whether it's a float, whether it's a Boolean, whether it's a car. Like at the end of the day, what we're doing is we're taking some complex concept and we're mapping it as a collection of attributes that can then be used fields that are all of the primitive types. So consider the following problem, whereby we design a class date to model a calendar date that consists of a day, month, and year. If we use integers to hold the day, month, and year, right? So that's a primitive data type that we'll rely on to say, okay, inside of a date, we have a day, month, year values. Then the day value is going to be more restrictive than the bounds of a legal int value. So for instance, it makes no sense to have a day minus 17 in a date, or a day of 7,081 or 70,081 or 700,081. Like, despite those are both legal integer values, they're not valid for a representation of the day in a date. And these are the issues we can end up seeing that can happen accidentally if we're not careful, is the idea that since we rely on these primitive data types that usually have a larger scope than how we intend to use them for our data model, then every time there's a mutation to our data model, we might want to ensure that the state of our data remains valid. So the valid value would be a day that's, say, between 1 to 30 or 1 to 31 or 1 to 28, depending on what the month is. And so even though legally any value could be there, we want to ensure it's a value that models what it means to be a day, a value that is representative of a month, and a value that's representative of a year. And just to highlight that, this month versus integer, the integer value could be anything. Any one of these is a legal value, but in terms of valid for our model, so that we stay consistent, so that our class will be reliable, then really month can only be between 1 to 12. And so since we're the implementer, we want to ensure that that's the case, that our class can never fall into an invalid state, because that would cause erroneous behavior across the software system. So again, we're going to be defensive about that. So what is the difference between using Java exception handling and using assert conditions? So we saw in the prior example, when I introduced the concept of defensive programming, that you can use asserts to cause an assert error to trigger if it fails to meet that condition. But there's also exceptions that we've seen last semester in Java 1, and maybe even some in this semester, certainly in this lecture. So when should we use exceptions and when should we use the assert keyword? So for example, in Java, which is the better approach? If I had a method public void do stuff where we passed in an object, do we assert object is not null, or do we want to do this? Public void do stuff where we're passing the object and we check if the object is null, then to throw a new illegal argument exception along with a message that, hey, the object was null. And so the answer to this question is that unchecked exceptions are designed to detect programming errors of the users of your library, while assertions are designed to detect errors in your own logic. So in other words, while you're designing your code, but before sharing it with other people to use, you would use the assert keyword so that you can verify while you're developing all of your methods and classes that they're working as intended, that they're following your preconditions and postconditions while you're testing them. You could do this alongside JUnit testing. Whereas exceptions are intended to be used after you've deployed your API, after you started sharing your code, so that other users will get an exception if a precondition is violated. So just a long answer for form of that is assertions are removed at runtime unless you explicitly specify to enable assertions when compiling your code. So Java assertions are not used on production code and should be restricted to private methods, since private methods are expected to be known and used only by the developers. Also assert will throw assertion error, which extends error, not exception, and which normally indicates you have a very abnormal error, like an out of memory error, which is hard to recover from, and you're not expected to be able to treat. So I will say that asserts are also useful. I hadn't mentioned this before, but asserts are also useful in those conditions where you can't JUnit test. So recall that JUnit testing tests a method and a class the way it would be used in the software system. But if you do have private helper methods, those private helper methods are not exposed to the JUnit tester. And so you can use asserts to ensure that any private methods are working as you'd expect, because then that would throw your assertion error and alert you. Okay, so to discriminate between asserts and exceptions, let's just take a quick look at asserts again. So Java assert statements provide some support for defensive programming. The form of assert I is greater than 0 is effectively translated into Java as this. So we'll have this code block that checks if this condition is not met, then throw a new assertion error instance. So if the program is run with but it will only do that if the program is run with assertion. So you have to manually tell if you're using assert keyword for Java to actually evaluate those asserts. Otherwise, it just ignores any assert statements. And so if you want the JVM to go ahead to run the code with asserts, you have to use the flag -EA for enable assertions. So by default, assertions are not checked, which is why you only want to use it while you're developing, because you have to manually toggle it on. Otherwise, you want to use exceptions for your defensive programming strategies. So however, this is exactly what we're saying. So exceptions take effect all the times. Asserts only take effect when we tell them to. So let's talk about exceptions. Exceptions, even if your classes are well protected, errors can still occur, right? So client code attempts to use your methods incorrectly by passing incorrect or invalid parameter values. Your code cannot perform the services it is meant to due to circumstances outside of your control as the developer. So your own code behaves incorrectly and or your objects become corrupted. So Java provides exceptions, both checked and unchecked, to be able to handle these situations. So the idea is that exceptions can represent unusual events that client code could handle, as well as errors. So it could be things like a finite data structure is full, or you can't add a new element, or you have like an attempt to open a file that failed because maybe the name was wrong or the path was wrong, or a network connection that dropped in the middle of a transfer, where then you would have to reestablish these connections. So these are all things that could cause your code to fail, but the client could potentially recover from. So it's not a flat out error. It's just an exception that you might have to change your methodology and attempt again. So the problem is that the object that detects the error doesn't and probably shouldn't know how to handle it, and that the client code that could handle the error isn't in a position to detect it. So our solution here is for an object detecting an error that throws an exception to the client code that catches the exception and handles it. So for instance, if a parameter is invalid, then the method cannot do anything sensible with the request, and so it creates an object from an exception class and throws it. And if an exception is thrown, then the runtime environment immediately tries to deal with it. So if it is an unchecked exception, it simply causes the runtime to halt with an error message. And if it's a checked exception, then the runtime tries to find some object willing to deal with it. So the method, for instance, carat throws a string index out of bounds exception, which is unchecked and hence causes the program to cease execution or crash. So your own methods and or constructors can throw exceptions if clients attempt to call them incorrectly. This is how your code can enforce rules about how methods should be used. For example, we can insist that the deposit and withdrawal methods from the bank account class are called with positive values for the amount. That's something we had discussed when we were looking at a bank account class. So the general mechanism is to check the parameters and if they're invalid in some way. So for instance, to create an object from class illegal argument exception, you would throw that object. Okay, so to give you an actual code-based example, suppose we have this bank account constructor here where that takes in some amount. And you would check if the amount is greater than or equal to 0, you would set the amount. And if it's not, then that would violate the precondition that the amount has to be a positive value. So then you could throw a new illegal argument exception, which is a predefined exception as part of the Java language. And then this constructor would go ahead and then use a string as a message that is delivered to the client code. And so throw conceptually is very much like return. So where a return returns a value that's declared as a return type inside of a method, a throw returns control to the client code with an object that is either of error, of class error, or class exception. In fact, both class error and class exception in Java implement an interface that's called throwable, and anything that is a member of the throwable interface can be a recipient of the throw keyword. Okay, let's go back to our predictable errors. So unchecked exceptions terminate program execution and are unchecked and are used when the client code must be seriously wrong. However, there are error situations that do not necessarily mean that the client code is incorrect, but reflect either a transient, predictable, or easily correctable mistake. This is particularly common when handling end user input or dealing with operating systems. For example, printers may be out of paper, disks may be full, websites may be inaccessible, or file names might be mistyped, and so on. So checked exceptions, methods prone to such errors may elect to throw checked exceptions rather than unchecked exceptions. Using checked exceptions is more complicated than using unchecked exceptions in two ways. The programmer must declare that the method might throw a checked exception, and the client code using the method is required to provide code that will run if the method does throw an exception. So with unchecked, you don't necessarily have to try to catch it, to catch the exception, whereas checked, you always have to try to catch the exception whenever you use that code. So checked exceptions typically happen with like IO exceptions, like when you open up a file, as what was mentioned, whereas unchecked might be an illegal argument exception. Okay, let's see here. With exceptions from the client's perspective, many of the Java library classes declare what they might throw a checked exception. Oh, I hope I didn't inverse that when I was explaining that before. Say for instance, if we look at our API here, this is a public file reader. So we're looking at the source code here. If we look at the source code for a file reader where we pass in a file, we might throw a file not found exception. So this creates a new file reader given the file to read from. And so the file not found exception that could potentially throw is going to be if the file does not exist, is a directory rather than a regular file, or for some other reason cannot be opened for reading. No, yeah, so this is perfect. This is what the API should look like. So this is the access type. This would be the constructor. This is the parameter. This lets you know it throws a file not found exception. This is the description of what this constructor does. This is the parameters, which are effectively our preconditions. So it requires a file object and the file to read from, a description of what that parameter is. And then if you do throw an exception, it should be part of the API so the client code knows what to potentially try to catch for. Okay, so some basic syntax from the client code perspective of how to recover if an exception is thrown their way. You would try to invoke the method that is something that might blow up. And on the instance that it does blow up, you catch the exception object, and then you can have some kind of recovery code inside that catch block. Here, the E is the exception object, which is the parameter. So in terms of semantics, you have your try block that attempts to execute. If no exception occurs, then it executes like normal. The catch block only occurs if an exception is thrown. And so when we define those catch blocks, you can actually define any number of catch blocks for any number of particular exception instances. So we might try to attempt to read a file here, and then this might result in 3 different exceptions that could occur. So the first that we would try, and you would try to catch these exceptions in the order that they occur at. So file not found exception would be the first. And if it's not a file not found exception, then we would move to the next catch to see if it's an IO exception. And if it's not an IO exception, then it would go to just the exception class. And so this is the most, you work from most specific to most abstract. And it's possible if that your recovery code is similar for different types of exception instances, you could also do a comma separated list inside of one catch block instead of having this kind of nested collection. And of course, if no match is made, then no catch is performed, and then it would appear that your software would just crash because you're not recovering from it. Okay, if code uses a method that might throw a checked exception, then it must enclose it in a try catch block. And so here's a more concrete example. So if we try to go ahead and create a new file reader, and we give it the file name that we want to read from and store that into a variable, a file reader data type, then if the code's okay, we would run that, but we could potentially need to catch the java.io.file not found exception, in which case we would recover from here. So if everything goes smoothly, the code in the try block is executed, the code in the catch block is skipped. Otherwise, if one of the statements in the try block causes the exception to be thrown, then execution immediately jumps to the catch block, which tries to recover from the problem. And what can the catch block do? Well, for human users, it can report the error and ask the user to change the request or retype their password or whatever so that you can fix it. In all cases, though, you can provide some feedback as to the likely cause of the error and how it may be overcome, even if it ultimately is just causes the execution to cease. So logging is clearly the most critical thing, just to alert other developers if interfacing with the end user, but if it's being reported to another developer, they understand why the exception occurred. Again, as part of that defensive programming strategy we've been talking about. And then finally, we've looked at the try block, we've looked at the catch block. There's also a finally block we can attach at the very end of that kind of sequence. And so the semantics here is that the code in the finally block will always execute, whether it was the try block or a catch block that that had executed. And so this is useful to guarantee execution of any kind of cleanup code, no matter what. A lot of this has to do with like closing a file, for instance. You want to do that whether you were successful in opening and reading from it, or whether for some reason an exception occurred while opening it. And so just a actual concrete example of what that finally block would look like would be this right here. So suppose that we have this public static void throw exception that throws an exception. We could try to do this risky code, system.out.println, and then throw a new exception. Well, that would then have to get caught here. So then we would have a system.error.println where we will then report or log what the exception was. And then in this finally block, regardless of whether it was a try, the catch, or the catch that had fully executed, we would then just report system.error.println finally executed and throw exception. Okay, and then finally, since we're talking about using exceptions in order to log any violations to the preconditions and alert as a courtesy the client code that something has triggered a wrong state or triggered something to go wrong inside of our implementation, we might want to be able to test that when we're JUnit testing, right? So we don't want to just test when we build our test cases, when we make our test plan to check those things that are valid. But if we have defensive programming strategies in there, we want to ensure that those work as expected as well. And so JUnit 5 does allow us to go ahead and test for exceptions. I believe when we went through JUnit as a practical exercise, I went through this already, but here is also that same bit of code. So if we want to say, for instance, test seconds inside of this test method, we could use assert throws, which is something that JUnit is one of the assertions that JUnit has, where we define the class that the exception class we're looking for, so illegal argument exception, and then we go ahead and use this lambda expression here, this lambda function, this unnamed anonymous method, where it will go ahead and execute the code that should cause that exception to occur. And then we will catch that exception here, and then we can assert equals. We can take the message that we intend to send to the client code and see if the thrown exception has that message. So I'm getting a question. What is the difference between system.err and system.out? Well, so system is a predefined package inside of it's a predefined, class inside of Java. And so some of the attributes, some of the properties that system has is streams that you can connect to that allows you to bring data or tokens into your software system, into your Java application, and to also send data out of your software application back to some other client code. So some predefined streams that you can use are system.out and system.err. Those are two different streams. One's designed for standard output that goes to the console. The other is supposed to go to system.err, which is used for error reporting. So system.err is used to print errors. System.out is just to produce non-error text to the console. So that's the only difference. You actually have two different pipes that you can send data out to, depending on whether it should be logged as an error or whether it should just be logged as standard fare output. And we'll learn more about output streams, or just streams in general, print streams is what we'll call those, as we when we talk about the IO and streams unit of this course, which will be a little bit later on. But you'll see it in practice, because some of the JUnit tests that I gave last lecture used print streams. So you'll get a chance to play around with them before we formally lecture about them, but we will certainly lecture about them because they're very important to know, especially when it comes to like writing to files, reading from files, or being able to serialize our in-memory data so that we can write that to file or send it through a network to a networked application. We do that all with streams. Okay, let's see here. Okay, some useful exceptions that you should be aware of is illegal argument exception, because that's typically, like I said earlier, if we're going to practice defensive programming, one of the most common manifestations of that will be for your mutator methods, the ones that allow client code to attempt to change the state of one of your instances of data that you're modeling, that you've developed, that you've implemented. And so if the client code attempts to use a value that would mutate the state of your data into something that would become invalid, again, thinking of like time, for instance, let's say you're creating a clock, and so the hour has to be in military time, somewhere between 0 to 23. Well, they couldn't give a negative number there, or they couldn't give a number higher than 23. That wouldn't make sense. So that would violate the way that you're modeling how a time works, how a time hour works. And so you can prevent that mutation, but not only prevent it, you can then alert the client code that they attempted to do something illegal to the state. And that way you're making your class super robust and resilient. You're ensuring that your class will always be in a valid state. And again, this is why we encapsulate. This is why we protect all of our data as private, because that allows us inside the class to have control on how the data gets mutated. And we can guarantee that the only mutation that occurs will keep it in a valid state and will prevent it from becoming an invalid state in terms of our model definition. Other popular exceptions are an index out of bounds exception, that's for arrays, a null pointer exception, that's when you expect a reference to an in-memory object, but it doesn't exist. It's pointing to null. An arithmetic exception, this is where some kind of mathematical operation can occur. And then an IO exception, or file not found, are going to be more or less related to your input-output conditions. So when we discuss programming by contract, we describe how to throw an exception to indicate an error, a precondition is not met, or other reason. So again, this is exceptions are useful because it allows us to defensively program and ensure that preconditions are met or not met. So for instance, if the argument is null, we could throw a new null pointer exception and alert our client code that, hey, we need a value for that. Or if the index is less than 0, or the index is greater than the size of an array, we can throw a new index out of bounds exception to say, hey, there's no such item at that index. Okay, a quick highlight on checked exceptions and unchecked exceptions. So checked exceptions in Java extends the java.lang.exception class, whereas unchecked exceptions extend the java.lang runtime exception. So since these are both defined in java.lang, you get access to them automatically. You don't have to import these particular exceptions. Now, exceptions that are not part of, excuse me, the built-in language, you'd have to import. So like, for instance, any exceptions for input-output operations, you might have to import java.io, and then whatever the exception is, you'd want to go ahead and throw or catch. So just to give you a quick perspective of what the class hierarchy looks like for exceptions, or just throwable in general, this is what it looks like. So you have this interface throwable, anything that is throwable, anything that is a member of throwable can be a recipient, can be a target of the throw keyword, which means you can exit out one method and return control to a client code, but that what's going to be returned is going to be either an exception object or an error object. An error object you can't recover from, right? It's going to, it's something that's non-recoverable. Exceptions are something that is unusual and that the client could potentially recover from. That's why you can do a try-catch block with them. And so with exceptions, you have these runtime exceptions. And so the runtime exceptions are typically the ones that you can go ahead and optionally look out for. They happen during runtime. So for instance, the class cast exception or the null pointer exception or the arithmetic exception or the index out of bounds exception. All these exceptions are going to be checked when you try to execute that block of code. And if the array is out of bounds, it's going to throw that exception at you. Whereas the input and output exception here is not a member of the runtime exception. So here you can have an idea that these like IO exception, file not found exception, these are all would be classified as your checked exceptions versus the unchecked exceptions. The unchecked exceptions execute regardless of whether you're checking or not, where these you have to check them. So if you choose to write a method that throws a checked exception, then this must be declared in the source code where you must specify the type of exception that might be thrown. So public void print file throws a java.io.file not found exception. So if you declare that your method might throw a checked exception, then the compiler will force any client code that uses that method to use a try-catch block. So checked exceptions have to go in try-catch blocks. Unchecked exceptions, it's optional whether you put it in try-catch block, and if it gets thrown, then it'll just crash your system. But you could still, but if it doesn't cause an exception to occur, it'll just run like normal. So this explicitly makes the client code responsible for these situations, for checked exceptions. So you're making almost a contract with checked exceptions where you're forcing the client to have to do a try-catch block. So again, with unchecked exceptions, any method can throw them without declaring the possibility. For unchecked exceptions, no need for client code to use try-catch. It causes the exception to cease, and it's used for fatal errors that are unexpected and likely to be recoverable and unlikely to be recoverable. For checked exceptions, these methods must declare that they might throw them. The client code must use a try-catch. It causes the control flow to move to the catch block, and it's used for situations that are not entirely unexpected and from which clients may be able to recover from. Use only if you think the client code might be able to do something about the problem. Okay, so some summary on exceptions and defensive programming in general. So programming defensively means making your code robust to unexpected use. Use the need to know principle, so only expose the parts of your class that your client classes need to know. Java exceptions provide a uniform way of handling errors, and exceptions may be unchecked or checked. So it's intended for usual or unanticipated conditions, so relatively expensive if thrown, free if not used. The guideline is used in situations where you're in a position to detect an error, but only client code would know how to react. And another guideline is often appropriate in cases where a method's preconditions are met, but the method isn't able to successfully establish postconditions, such as the method can't do what is requested through no fault of the caller. So that's an alternate reason why you might want to have your exceptions be thrown. If preconditions are met, but some reason might cause this edge case to result in an exception, or you can do it for preconditions and as a courtesy alert your user that something had gone awry. Okay, so we've covered a lot of slides. Slides kind of give the theory of everything, but let's move over to some implementation really quick. So here I have this demo project I assembled. There we go. Wait for it to pivot. Okay. No. Nope, that's not it. That is okay. Got some lag time here. Okay, perfect. Okay, so I have this demo here. Let me get my chat in this window. Okay, let's open up defensive demo. Just wait for that to load in. Okay, perfect. Let's close all this. Okay, so inside of here, we have a IntelliJ project where I'm going to go ahead and create some basic classes that represent, like I was saying before, time. So suppose we want to model time. And so we're modeling time with hours, minutes, and seconds. And so we want that encapsulation so that we have sole control over the state of hours, minutes, and seconds, because since they're labeled as integers, they can have any value, but for the sake of our modeling, the value of hours has to be between 0 and 59. 0 and 23. The value of hours has to be between 0 and 23. The value of minutes has to be between 0 and 59, and the value of seconds has to be between 0 and 59. So if we want to ensure that our class is correct and never becomes an invalid time, we want to defend against that. So we have a basic constructor that takes in hours, minutes, seconds, and we'll call this helper method setTime. Our setTime method, hours, minutes, and seconds, invokes these helper methods to set an hour, to set a minute, and to set a second. And see in here, this is where we're going to use defensive programming to ensure that our time never goes into an invalid state that violates our modeling, the way that we're modeling time. So here, when a client code passes in a value into hours, we'll check if hours is outside of the conditions that we stipulated. So if it's invalid, so we're going to see if hours is less than 0, or if hours is greater than or equal to 24. And if it is, then we're going to throw a new illegal argument exception. We're going to pass it the message to alert the client code, hey, your hour must be 0 to 23. And if it doesn't throw this, then we can assume that, hey, this is a correct hour. This is a valid value of an hour. This integer is complicit with how we're modeling an hour, so we can set that to our instance variable. And so the same could be said for how we set minutes. We'll check to see if the value passed in as minutes violates what we claim to be a valid value. So if minutes is negative, or if it's 60 or greater, then we're going to throw an illegal argument exception. Otherwise, we're going to go ahead and set that. And then we'll do the same thing for set seconds, where we will check to see if it violates the precondition, and if it does, then we will throw that illegal argument exception as a courtesy to the client code to let them know why their code won't work. And then finally, if we don't throw that exception, then we will then set the seconds. So just a very simple class here. And related to that, we have another, like a date class here, right, where we have and I believe these were implemented in Java 1. So I'm just cribbing on what we've already done in the previous semester. So here we have an array of days per month, so that we know whether a month has 31 days or 28 days or 30 days or whatever. And so we can model a date as a year, a month, and a day, all primitive data types as int. So again, ints have such a broad range that we need a specific subset of them to represent a valid value for year, or a valid value for month, or a valid value for day. So when we go to implement a set date, and we have these helper methods that are going to check each individual attribute, well, let's say we get to define what's valid or not. So let's say that any year but before 1900 isn't considered a valid date in our date class. So then we would throw an illegal argument exception. The year must be before 1900. Same thing with month, where we might want to check to make sure the month is not negative and it is 12 or if it's 13 or higher. And then with day, we would check to see if the day that's passed. Well, in order to check the day, we have to know what month it is, right? So we would get the value of the month, and then we get whatever the value of the day is. We would index the month to see if day is greater than the number of days for that month, or if day is negative, then we would throw this illegal argument exception. In fact, this is a simpler class. It doesn't even check for leap year. You'd want to do an additional check if it's February to see if it's the 29th or the 28th. That's a valid day for leap year. Okay, so that's just an example of how from an implementer side, we would want to make use of exceptions in a defensive programming strategy to be a companion to our design by contract. So we define our preconditions, we define our postconditions, and then we can check the preconditions and throw exceptions to client code to make a very robust API. And so you're probably already familiar with the usage of all of these from a client code perspective, because as you have been developing code, you've probably encountered exceptions before. And they've probably been very useful for you to be able to debug your code and get it working. And so all we're talking about is designing our own APIs with these same kinds of tools in place to allow other client code that will rely on our code base to be able to have those same advantages. Okay, so to test this out, now if I'm building these so I can share as part of my API, I would want to do JUnit tests on those. So I would have, say, for instance, this time test class, which is a JUnit test class, where I import all the assertions, and then I'll go ahead and import the fully qualified annotations of test and before each, so I can just use those. I'm not setting anything up here, but you can see my test methods. I'm going to test the seconds, the minutes, and the hours. And just like in the slides, if I wanted to test the exceptions, just to show you that I can do that, I would use the assert throws, which is part of the assertions here. I got it imported here. I give it the type of exception I want to look for, and then a anonymous method that causes that exception to trigger. So here it's going to, because seconds is 100, it's going to cause an illegal argument exception to occur. I'm going to catch that and save it into this thrown variable here. And then I'm going to assert equals that the message, that the expected message is seconds must be 0 to 59. I'm going to check the exception that was thrown and get its message and see if it's the same thing. So yeah, we can go ahead and test all of our exceptions in our software in the same way. Make sure that this one here, if we pass minutes as 100, that we get minute must be 0 to 59, or here, hour must be 23, that if we make it 24, that'll occur. And if I go to the top here and I run this code, you'll see that it's going to have all of my tests complete and pass. Now, let's look at my date test really quick. So on the flip side of that, if I try to do these things, so let's say I have get day, get month, and get year, and I try to create a date where the day is 365. Well, clearly that's a violation. And notice, I'm just going to try to do that. I can do the same thing here, create a date where the month is 120. Clearly a typo. I'm probably meant to do a 12 and I put a 0 afterwards, or I put a negative sign in front of the year here. So if I try to run these codes, I'm going to still get those exceptions. I'm going to fail the JUnit test. But the nice thing about this is the JUnit test inside the console will illustrate what went wrong with this. So it'll say, oh, that was an illegal argument exception and it was an invalid day, or the year must be before 1900, or the month must be between, well, it should be 1-12. So here, if we don't catch it, we won't pass the test, whereas these allowed us to pass the test and actually check the exception and claim that it's working properly, where here, we're trying to build something, it fails it, and then we can see why it failed in here. So it gives us the data that we're looking for as client code. So this is just two different approaches of how we use JUnit tests to test a class in isolation of it being in a main method or it being inside of an app or some other launching application inside of Java. And so to see how client code can then try to catch these exceptions, let me show you this exception example I have. So just to put this, so Here, I'm going to import the scanner object. And so the scanner object actually has an exception that it can throw. But since the scanner exists inside the java.util package, the exceptions that the scanner object has customized, because you can create your own exceptions as well. And so the util package has custom exceptions that extend the exceptions class. So one of those is the input mismatch exception. So we need, if we want to try to throw that exception, we have to import it into our source code. So here we have this public class exception example. It has a main method. Inside our main method, we're going to go ahead and create a scanner instance that we'll call input, that's going to look at the system.in stream, the print stream. Here, we're going to go ahead and create a loop control variable and set it to true. We're going to do a do while loop. So inside of our do while loop, let me see if I can't bring this down a little. We're going to try. So we're going to do this try block. We're going to display or prompt the user, hey, enter a numerator. And then we're going to, from our scanner object, we're going to get the next int and save that into numerator. Then we're going to prompt the user to get a denominator, to enter a denominator. Then we're going to use our scanner object to go ahead and pluck the next integer from the print stream into this variable denominator from the system.in. And then we're going to do this arithmetic operation where we take the numerator and divide it by the denominator. And then we're going to produce a result. And then we'll print the result using a printf, where it's the numerator, the denominator, and the result. And then we'll set the loop control variable to false, which will exit us out of this do while loop, right? This is the looping structure. So we do the body of the loop in a do while loop, and then we evaluate to see if we do it again. And then we're going to do two catch blocks. We're going to attempt to catch on the instance of an arithmetic exception, and we're going to print out, hey, an exception occur. You can't divide by 0. Or a input mismatch exception, where we'll print out to the user, the input must be an integer. We get this if the input is anything other than an integer for next in. So if it's a string, for instance, that's going to throw an exception. We can actually recover from that. And then what we'll do is we'll put that it must be an integer, and then we're going to go ahead and remove what's currently the tokens inside of the system.input stream, and then reset it so that we could try to get a new value. So let's see what this actually looks like. And if you have any questions about what's happening on this code, please ask. But I'm going to run it now. So let's run this method. We're going to run that. And so inside of my terminal here, inside my console, it's going to do the system.outs. It's going to say enter a numerator. So let me get it to work as expected first. So let me do 12, and then I'll do 13. And so 12 divided by 13 equals 0 with integer division. Okay, that works as per expected. So now let's do some of these edge cases that should throw exceptions and see how we can recover based off of our client code implementation here. So here I'm going to do 12 as my numerator, and for my denominator, I'm going to do 0. Well, 12 divided by 0 is going to cause an arithmetic error exception to occur, right? So it's going to say, hey, an exception, you cannot divide by 0. That means I caught that exception here, arithmetic exception. But since then I recovered because we only set the loop control variable to false at the very end of the try block. So at any time while executing the statements in our try block, if an exception occurs and we stop at that block of code where the exception occurs at and we fall into the catch block, then the loop control variable is going to be true, and it's going to jump us back up to the top, and it's going to allow us to restart. So this illustrates how we built an application that can now recover from an exceptional behavior and keep working. So here it gave me this important note, hey, you cannot divide by 0. So let me try that again. 12 as the numerator, and let's say we do 5 as the denominator. Well, 12 divided by 5 is equal to 2 in integer division. Perfect. So let's try testing this out again. But it's not just arithmetic exceptions that might occur. It could also be input mismatches going into the scanner object. So let me wait for it to run. Okay, so for instance, if I just enter the letter Q here, it's really expecting an int, right? We're calling next int. So the scanner is going to throw an exception, but we can catch it. Exception input must be an integer. And so since the loop control variable wasn't set to false, the do while loop is going to set me back up to the top, and I'm going to rerun the application. So it feels very fluent from a end user perspective. So here, let me do this again. 12 divided into 3 is equal to 4. Perfect. And that's an example of how we might use exceptions on both our side, where we throw them a new exception to a client code, and how we might, as a client, anticipate an exception, try to execute code that is risky or could result in exceptional behavior, and then try to catch that exception and do something with it that we can recover from and still have our application produce a result, process and finish out and exit on its own terms, as opposed to crashing. So is there any questions about like these concepts of defensive programming and using exception handling to go ahead and defend your software on top of using a design by contract approach? Was everyone familiar with exceptions up to this, or did this help fill in any gaps that you might have had from Java 1? So I know that these concepts theoretically were covered in Java 1, but I'm not sure to which degree. Okay, excellent. And so that's going to be our discussion on exceptions.